Hey everyone, welcome to week 6 of mini lecture. Today we'll be covering dynamic programming, which is a very exciting concept. It's another general strategy, overarching strategy that helps us approach a very large class of problems. So the previous two, I guess, large strategies are greedy and divide and conquer we covered. And for each, we talked about the strategy and general pattern of a problem that can be solved by either of these. And then we built up a repertoire of classic problems, for example, like FFT or graph algorithms, Dijkstra, Spellman-Ford, all these really classic examples. And we'll do the same with dynamic programming. Basically, we'll cover some general strategy, some intuition, but then we'll have two amazing tutors joining us today who will each be covering one of the most important and classic examples in dynamic programming. And these problems will sort of be the bread and butter of this mini lecture, where the goal is, well, with these examples, you can develop some intuition and be able to attack other problems that you encounter with the DP strategy. And I hope in doing some discussion problems or homework, you'll start noticing that there are similarities between new problems and the classic model examples that we present here in mini lecture. So let's jump right in. But before we do that, if you miss Neil, worry not, you'll see him in a midterm walkthrough video, and he'll join back with the mini lecture next week. So let's start with a motivating example. Let's just recall a directed acyclic graph. So these are directed graphs that don't have cycles. And I want to know, how do I find the longest or shortest path to every single node? So we can give a nice solution, actually, without having to do Dijkstra's or Bellman-Ford, because directed acyclic graphs are very special. Maybe you can remember from our previous discussion of graph algorithms that every single DAG or directed acyclic graph can be linearized. So we can use the toposort algorithm to list out all of its nodes or vertices in a linear order such that all of the edges go from left to right. So there are no back edges from the right to left. And this is very nice because suppose I take some node D, I'll put a star, I'll put a star at D. If I want to find the shortest path to D, well, I better get to B or C first, right? Because these are the only two ways of getting to D. So then I can write down the following, that, the distance to D from S is our source, is equal to the minimum of two things, right? You either go to the node C first, so distance to C, and then you add however long it takes to get from C to D, which is 3 here, or you get to B first, so distance to B, and then you add the distance from B to D, right? So these are the only two possibilities, and we've written down a determined like equation for what this could be. So if we had known what the distance to C and the distance to B would be, then distance to D would be solved. So you might be thinking tree recursion right now. This looks so much like tree recursion. You're just calling the same function on its two parents. But we're actually not going to do tree recursion here. So tree recursion will start from D and sort of push backwards, push to the front by going to parents. But we'll go the other way. We'll start from the very beginning. So here's what we'll do. Let's see. Let's start with S. So the distance to S is very simple. It's 0, right? You're there already. You don't need to go anywhere. And then we can look at the distance to C. This whole linearization thing tells us that I only need to look at nodes that have been covered beforehand. There are no paths from a node that I haven't explored back to C. So I only care about any paths that started with nodes to the left of C. In this case, we only have one parent of C, which is S. So doing something very similar to this equation here, I can just say that, the distance to C has to be distance to S plus the 2 from S to C. So I can fill in that this to C is 2. Now we look at A. A is a little bit more complicated than C, but we can still write the same idea, right? Distance to A is you take the minimum, and then you either get to A from just S, So that's distance to S plus from S to A, which is 1. Or you get to C first, distance to C plus 4. Right. And I already know what the distance to S and C is, right? We already calculated this. And the magic here is that regardless of what node I am on right now, I can always look at the nodes that came before, and those are the only paths that lead to the current node. And that's the whole like magic of linearization. You don't have any edges that lead backwards. So then we can say, well, distance to S is 0, 0 plus 1 is 1, and then distance to C is 2, 2 plus 4 is 6. So the 1 is smaller, so I put 1 here. And we can keep going with this, right? For B, the only choice I have is to get to A first, so I just take the distance to A and add 6. As for D, I can either get to B and add 1, in which case it's 8, or I can get to C and add 3, which is 5. I take the smaller one, so I get 5. And as for E, I can either get to B and add 2, or get to D and add 1. So we can say 6. Right? So basically, what happened here is, with each vertex that we're exploring, we get the answer almost instantaneously. We only have to look at what the nodes that lead to the current node, and then since we've already stored what those distances are, I can just take the stored value and add whatever I have on the path to the current node. So compare this with the recursion. If we had done recursion, then perhaps we'd have to do something very complicated. And I'll try to draw this out. So if we had chosen to do recursion, then if I wanted to get to E, then, well, I better calculate the distance to D and the distance to B. To get the distance to D, I better get the distance to B and distance to C. And B, I get to A. And you can see that like there's already repetition. Without storing things in this sort of data structure, we have to calculate the distance to B multiple times. And then you can imagine that as we recurse more and more, there are more and more repetitions that are sort of unnecessary. So by starting from the front rather than from the back and pushing through recursion, we're able to store each subproblem, and then each current problem that we need to solve is just you just need to read some results from previous subproblems and then add a little bit of change to it. So the algorithm here in, an algorithm in algorithm notation, I guess, looks like this. So I initialize all of the distances to infinity as we do in every other shortest path search algorithm. And I set the distance to S as 0 because we're starting from S. Then for each vertex, for each node, in linearized order, we calculate the distance as the minimum over all of the possible parents, plus this is the distance to every parent, plus the distance from that parent to the node. These are just edge weights. And the reason we can do this very fast is because we're always guaranteed that regardless of what node we're on, every previous node has already been stored in this list. So there are a couple of things to note here. I may be repeating myself a little bit, but these will become very important as you analyze what are the common themes in dynamic programming. One thing is that we're storing values. We're memoizing the solutions to the smaller problems so that the bigger problems can reference the stored values. Another thing to know is that we only have to calculate each distance once, and we call these our subproblems. Each subproblem is very similar, and the solution to each subproblem is only dependent on its previous subproblems. And this is, the sort of the soul of dynamic programming, is that through memoizing previous solutions to subproblems, we're able to reference those instead of having to recurse. All right, so that's the motivating example of shortest distance, and you can see that you can sort of do this. It doesn't just have to be shortest distance. I could do this with longest distance, and I just change this right here to max, or I don't know, I can do my favorite distance by saying, I don't know, I want the product of all the edge weights that come before it. Something like that. You can do this with like just about anything. And the idea is, regardless of what you do, you have this like theme of storing values, of creating subproblems, and of referencing those subproblems in each like larger problem. Okay, so I'll pass it now to our tutors to go through two more very important examples.
Hi everyone, I'm Alicia. Today I'll be doing a mini walkthrough for the longest increasing subsequence. So this is one of the first class examples that we're going over for the dynamic programming part. I personally find it really interesting and super useful, not only in job interviews, but just a way to think about these problems. Say you have an unsorted array of any numbers, positive, negative. Feel free to think about it as an array, but like you're just given this input. So we're trying to find the length of the longest increasing subsequence, which in this case would be 3. I was going to talk about the difference between subarray and the subsequence. So a subarray is contiguous blocks. So this example that I gave, it is contiguous because it's one specific part of the array without any like breaks in between. However, if I were to do this example, if I were to be looking for the longest increasing subarray, I would be getting 2, 4, 5, which is length 3. However, if I were to find the longest increasing subsequence, we have 1, 2, 4, 5, which actually results in a length of 4. Just wanted to make that clarification. And also this kind of leads to why our problem is sort of more difficult than if it were a subarray. I'm sure you've heard of this sort of way to think about it in 61A, maybe. I think the way they taught it was that at each element or at each index, if we think about it as an array, we have to decide whether we want to keep it in our final resulting increasing subsequence. You would like be calling recursion all over and over again. As you might have seen in your textbook, say if I were to pass it into the function of L of like, say index 5, I would be like recursing through all of these actually. So I'll be looking at like L4, L3, and then when I go to L4, I would also look at L3 and everything following it. And when I go to L3, I'll be like looking at L2 and like L1, for example. And the tree just like grows on, and it is actually polynomial in height, but exponential in the number of nodes. So for this very seemingly simple problem, we actually get an exponential runtime if we were to use recursion by itself without any dynamic programming. So this is where dynamic programming comes in, because say we were going down this recursion tree. Okay, oh cool, there's a pointer. So when I come here and I go to L4 and I go to L3, I will be saving these results as I go down, for example, this path, so that when I go to L3, I can just look up what I saved when I was going down this path, because I realized that these two results are the same, they're duplicates of each other. Think about like the Fibonacci example. These are pretty similar like recursion trees, and we're just like trying to find a way basically to cache previous computation results. And that will be proven very helpful, and it will help us reduce our runtime. In lecture, in the textbook as well, they built this array into a graph such that for any index I that's smaller than any index j, so if I were at an index that's like before another one, my element at that array or at that index is less than the element at index j, then I add an edge. Let's just take this simple 1, 3, 2, 4, 5 example. Edges going to actually all 4 of this. And when I get to 3, I'll be drawing edges to 4 and 5, and then 4 to 5. This might be reminiscent of like Dijkstra's. So like when you're at say like 4, you look back at like an edge 2 node and then see what's the length at that previous node, and we want to like add 1 to it. But the reason we don't consider if we're going to include or not include 4 is because we are considering every single path up until our current node. So the selection of whether or not we want to be including a node is actually coming when we get to the next, and then we like go through all the previous nodes and then see like which ones have edges leading towards you, because that means that that number is smaller than my current number. Yeah, I think using a graph representation is pretty intuitive. just under the cover, I would say this is what's going on. So at every node, you look at all nodes before you, and you cycle through all the nodes that are smaller than you, and you like pick the maximum longest increasing subsequence that's like saved at that node. And since we are just like going through a one pass from left to right through the sequence, like we are guaranteed to have result already saved there. Yeah, we're just going in order. So it's sort of building bottom up. I think of it more as like a greedy approach, because at every node, you're just looking at the best option at that node. So like when you get to the end, you know that you have all the options and you just go through all the nodes if they're less than you, and then pick the maximum. So the way I would formulate this in an equation is at like say L being our function, index I, we like just update L of I to be 1 plus the maximum of Lj, where j is less than I and the array element at j is less than the array element at I. You don't have to think about this as an array necessarily, but I'm just saying this just for like notation. What you will do is have a hash map or an array. I'm good with array because like your info is an array and you want to just be saving one number at like each node of like the maximum until that like node. So I'm good with like just saving my result in an array. So I can be saving like L of I here. This is just we can start at 0 and we won't have to use it, and then like 1. If you ever have to like code it up, it's definitely something to consider. Going back to this tree, right? So when I'm at like L2, I can just look at L1. And when I'm at L3, I don't have to recompute L1 and L2 again because I can just look it up. And each lookup is like constant time if you're using like an array or a hash map. And when you're at L5, you can just look at L4, L3, L2, L1. We don't have to go through every part of this subtree every single time we make a call. That's just like a lot of extra work. Just to help you see how it has improved, maybe you can pause the video and like work it out on your own, but I'm just gonna go over like the runtime if we were to use DP. When I'm at index 1, I look at technically 0 element before me. When I'm at index 2, I look at 1 element, like up to 1 element before me, and you look at length 2, and then length like up until n minus 1 when you're at the last index. So this is a arithmetic sequence from like 1 plus 2 plus 3 minus 1 if we want to be like very strict about this. This would just come down to quadratic runtime. Even though it is quadratic, it's still a pretty big improvement from exponential. And it's kind of bad because it's not even like 2 to the n. I would say like bigger than 2 to the n because like it's not like Fibonacci where it's 2 to the n, but this one has like more branching at some of the levels actually. So very significant improvement. That's why we use dynamic programming. If you want to think about it in recursion, we don't save our results, but in our DP methods, we do save it. So in a way, it's like a space and time trade-off. So right now we're just taking up more space so that we're spending less time to like recompute these results. Previously, we didn't really have to like save anything. So like space is pretty much like constant / non-existent, even though like you probably have a pretty deep stack. Here we're like splitting the work across space where we like actually save results and then like looking at previous entries. And your textbook at the end also mentions instead of the length, the longest increasing subsequence, the actual sequence itself. That is also pretty straightforward. So instead of saving like just an integer in say like an array or a hash map, you would be saving the actual sequence that you have up until Li. Right. So one thing that you can do once you're at the end of the array, when you're at the end of the like computing the entire like DP, you can either like make another pass through the array, like just to like return the maximum of the cached like results, or you can just keep like a global running maximum. So you update it every time you're at a new node. So same with the sequence. If we weren't looking for just an integer, we instead of saving Li equals to 1 plus max L of j, we can be saving Li max of len of Lj, if that makes sense, of Lj and your current element. And you save it in the cache. Hopefully this isn't too confusing, but just an aside. few takeaways. Hopefully that was kind of helpful. It is a very new topic to probably many of you. It was really new to me when I took this class and learned about DP, and it took a while to develop intuition. Maybe you like looking at code, and maybe that would like kind of help you understand what's going on under the cover. Feel free to like look it up. Trusting the recursion is definitely part of it, but instead of trusting the recursion, you trust like whatever results you computed before. So that's basically the new way to think about it. And with that, that's pretty much all I wanted to cover for lists or longest increasing subsequence. Leave a comment or like just ping me if you have any questions. All right, see you next time.
Hello, everyone. In this segment, I'm going to be going over the edit distance problem. The edit distance problem is an interesting problem because it's used in spell checking, but it also has applications in things like biology for things like DNA sequencing. So it's going to be a good problem for us to analyze using dynamic programming. So in the problem, we're given an input of two strings, x and y. Note that these strings do not need to be of the same length. They can be different lengths. And then our output is going to be the minimum number of edits needed to transform the string x into the string y. And what do I mean by edits? Well, what I mean by edits is just one of three things. So either we can insert a character, or we can delete a character, or we can substitute one character for another. So those are the only three operations we're going to use, and we're trying to figure out what is the minimum number of these operations that we can use to transform x into y. So this gives us some notion of a distance between x and y, or how far apart these strings are. So as an example, I'm going to use, let's say the string x is the string code, and the string y is the string word. So one way to transform code into word is, let's say we just delete every character from code. So delete the C, delete the O, delete the D, delete the E, and then we would insert the four letters in word. So we insert a W, we insert an O, we insert an R, and then we insert a D. So again, this top string is X and the bottom string is Y, and each vertical segment here represents a change to a certain character. So in this case, the C gets deleted, and in this case, a W gets inserted. So this uses 4 deletions and 4 insertions. So this uses 8 edits total. But this is not the most efficient way to do this. We can do this using fewer edits. So let's say we had strings x and y again. So let's say instead of deleting a C and then inserting a W, we use one operation to substitute the C into a W. So again, substitution is one operation. The O appears in both words, so we can keep that the same. We don't need to change that in any way. And then we can insert an R. This gives us WOR at the bottom. And then again, there's a D in both words, and those happen to align, so we don't need to change that. And then we can delete the E in code. So then this uses one substitution, one insertion, and one deletion. In other words, this uses 3 edits total. So 3 would be the edit distance between the strings x and y. So just sort of elaborating on what this notation means. So whenever you see a letter at the top followed by a blank at the bottom, this is a deletion. whenever you see a blank at the top followed by a letter at the bottom, this is an insertion. You're inserting the letter A. And then whenever you see two different letters at the top or bottom, this is a substitution. You're changing A into B. And then when you see two letters of the same on top of each other, this is no edit. So there's no change being applied to that specific character. So our goal is to minimize these three. So this is a problem that we can solve using dynamic programming. Now, remember, in dynamic programming, we always want to try to look for what kind of subproblem we can break this down into. Remember, the point of dynamic programming is to try to break down a problem into subproblems such that we can build up a solution to the bigger problem from the solutions of the smaller subproblems. So in this case, one logical subproblem to use, because we're dealing with strings, is substrings. So let's say instead of finding the minimum edit distance between code and word, we can find the minimum edit distance between some substring, let's say CO and WOR. This might be a logical step, so we're going to try it. So the subproblem we're going to solve, we're going to denote by E of I and J, which is, this represents the edit distance, the minimum edit distance between the strings, between the substrings x1 through I and y of 1 through j. So this is the first I characters of x and the first j characters of y. So, okay. So we have this subproblem. Now we need to figure out how we can define a recurrence relation. Remember, in dynamic programming, we always want to try to find a recurrence relation. So let's say we had a subproblem I, j. So the first I characters of x and the first j characters of y. Now we need to find some minimum, and we can think about what the previous edit would be. So the previous edit could have been a deletion, it could have been an insertion, or it could have been a substitution. So we can use this, we can say it's the minimum of a certain number of things. Now, let's say the previous edit was a deletion. In this case, if we deleted a character from X, then that means that uses one edit, so we'll add a 1, plus the previous subproblem would have been just the first I minus 1 characters of X, and then we deleted the last character of X, so therefore the edit distance here would just be I minus 1 and j. Now, if the previous operation was instead an insertion, then we would insert a character y, and then we can say that the minimum edit distance between I and between x, the first I characters of x and the first j characters of y, is going to be 1 plus e of I and j minus 1. Notice that j I and j minus 1 is the number of edits needed to transform the first I characters of x into the first j minus 1 characters of y, and then we insert one character to get y, the substring y from 1 to j. So again, this is a deletion. I'll use a different color here. This is a deletion, and this here is an insertion. And then what we also have is substitution. So a substitution also uses one edit. And then when we substitute the next character of x into the next character of y, then the previous subproblem would be the both substrings minus the character that we just substituted. So it would be 1 plus e of I minus 1 and j minus 1, where this is a substitution. But of course, this is only if x of I is not equal to y of j, meaning the ith character of x is not the same as the yth character in j. When the characters are not the same, we need to make an edit. But when the characters are the same, then we don't need to make an edit at all, and we can just use the same number of edits that we've had previously. So it would be equal to e of I minus 1 and j minus 1 if x of I equals y of j. So in reality, these are the two cases that we're considering here. So we can think of this as each problem, e of ij, is dependent on at most three other subproblems. So e of I minus 1 and j, e of I and j minus 1, and e of I minus 1 and j minus 1, also used here. So we can remember that in dynamic programming, we can represent the problem using a DAG. So I've sort of drawn a grid out here. Notice that we start from I equals 0 and j equals 0, that when one of the indices is 0, we're talking about the empty string. And then I've written the characters here across, so code and word. So in the top left corner here, this represents e of 0, 0. And then in the bottom here, we have the solution to the problem we're trying to figure out, which is e of m and n. And then everything in the middle here are subproblems. Every circle here is a subproblem e of I, j. And remember how we said that e of ij depends on the results of three subproblems, e of I and j minus 1, e of I minus 1 and j, and e of I minus 1, j minus 1. So all three of these can possibly affect the result of e of ij. And this recurrence relation holds for all of the circles on this graph. So we need to think of an order such that we solve all of the smaller subproblems first before solving any of the larger subproblems. So before we solve e of ij, we need to solve for these three subproblems first. So we need to go in an order that makes sense. And in this case, one order that would make sense is just go across in rows. This would ensure that we're not solving any problems before solving the subproblems that it's dependent upon. So this is a topological sort of this DAG. Alternatively, we can also go down in columns, which is probably how I'm going to write my algorithm here. So we just need to establish an order, and then we also need to establish some set of base cases. And in this case, the base cases are going to be everything where either I is 0 or j is 0. This is because these problems do not have a smaller subproblem to rely on. So this is a separate case that we'll need to deal with separately. But when one of the strings is the empty string, let's say if x is the empty string, then the only thing we can do is just keep adding all of the j characters in y. And similarly, if y is an empty string, then the only thing we can do is keep deleting characters in x until we get the empty string. So in either of these cases, if j is 0, then e of ij is just I, and then if I is 0, then e of ij is just j. So now that we have our subproblems and our recurrence relation, we're ready to start writing our algorithm. So our algorithm here is, so remember the function edit distance takes in two strings, x, which is a length m string, and y, which is a length n string. So first we'll take care of our base cases. So for I going from 0 to m, we'll have e of I0 equals I. And then for j going from 0 to n, we have e of 0j equals j. And then now we do our recurrence relation. So for I going from 1 to m, and then for j going from 1 to n, so for every ij pair, e of ij equals the minimum of either an insertion, so whatever it took to get to I minus 1 j, or I'm sorry, this is a deletion, plus 1, and then e of I and j minus 1. This is an insertion. And then for substitutions, we would use e of I minus 1, j minus 1, plus I'm going to use diff of I, j. So if the characters at I and j are the same, then we don't need to make any edits. So diff of ij is just 0. But then if they're different, we would need to make a substitution. So what we're returning in the end is e of mn, which is the edit distance between the entire two strings x and y. So again, like, let me just make a note, diff of ij equals 0 if xi equals yj, and then 1 if xi is not equal to yj. This means we need to use an edit to make a substitution. So in total, you can see that this algorithm takes a runtime of O of m times n, because that's the number of subproblems we have, and each subproblem takes only constant time because we're taking the minimum of 3 values. So therefore, the runtime is m times n. So this is a good example of how we used dynamic programming to solve the edit distance problem. Thank you.
Hello again. Before we end mini lecture, I want to just give a few guiding questions that I like to think about when I'm approaching a new problem with dynamic programming. And something that I encourage you to do as exercise after you finish watching this mini lecture is to answer these questions for the examples that we covered in this mini lecture. it'll probably help you just see the uniting themes between all of these algorithms. So the first thing is, what are the subproblems I need to solve the general problem? And something related to that is, what do I need to store? Like, what kind of information do I need to store for the subproblems? The second is, once I've identified all the subproblems, where do I start? What are the simplest subproblems that we can calculate first? And the next question, or the last question, is after I have all of these subproblems and after I have all the solutions to those subproblems, how do I combine them to get a solution to the general problem? Okay, awesome. With these questions, we'll end mini lecture here. So if you have any questions, post on the Piazza thread, and make sure you think through these problems for all the examples you cover in lecture as well as in the textbook. All right, bye.